All right. And I want to start working one of the practice problems that we've got. I'll dim the lights briefly so you can read this. This is actually some data from the 1950s. Now, for those of you that don't remember this part of US history, in the 1690s, a guy named Jacob Pastorius got permission to settle in what's now the state of Pennsylvania. It was a British colony back then, but Pastorius was German, and he was the leader of a Protestant religious sect that was getting persecuted. In the earlier 1600s, Europe had been absolutely trashed by the 30 Years' War, this terrible war of religion between Protestant and Catholic countries. There were various Protestant sects in Germany that did not get along with the Lutherans very well. They were being persecuted. Germany had lost in some places half of its population because of war, disease, and famine. And a number of these Protestant breakaway groups were ready for a way out, and Pastorius negotiated the right for them to settle in what's now Pennsylvania, and they became a population known as the Pennsylvania Germans, some of whom still speak a German dialect and maintain their language and their culture. You see a lot of Pennsylvania German stuff if you go up to, well, it's now eastern Pennsylvania around towns like Lancaster. There's actually a town in the Pennsylvania German area called Intercourse, which originally just meant, interactions, dealings, good place to do business. But now I think they lose a lot of money having to replace their signs, because I think every frat house on the East Coast has a stolen "Welcome to Intercourse" sign. Incidentally, there are nearby towns called Paradise and Fertility and Blue Ball. Blue Ball was actually called that because there used to be an inn, like a, motel and restaurant that had a blue ball as its sign hanging out. But you can pretty much write, the jokes pretty much write themselves. You have to go through Intercourse to get to Paradise, but if you want to avoid Fertility, you're stuck in Blue Ball, and I'm sorry, I'll stop. I don't know if it's creating a threatening atmosphere, but it's creating a very juvenile atmosphere. Right. So there's lots of these German Protestant sects still in Pennsylvania. They have their own customs and their own ways. Many of them still speak German, at least at home. They're not hostile, but they can be a little bit suspicious of outsiders. The group that you probably know best would be the Amish, right? You've heard of the Amish. They're the ones that are very rigidly limited on what modern technology they will accept. So they still drive horses and buggies. Yes? All right. They still raise barns, build them completely by hand, that sort of thing. There's also, of course, the Mennonites. That's another one. And there were various other groups, the Schwenkfelders and the, I don't know what else. And this question's about the old German Baptist brethren, who were affectionately known as the Dunkers. So called because they believed in baptizing by immersion, right? Instead of sprinkling or pouring water on somebody's head, you take them into a pool or maybe the river and, completely shove them in and say, I baptize you in the name of the Father and the Son, and hold your nose. Amen. That's not really what they say. Anyway, in 1950, there were about 3,500 Dunkers. They're not as strict about their lifestyle as the Amish. They're allowed to use some technology, but they tend to be isolated from the mainstream. They usually marry within their community, or at least they did in 1950. It may be a bit different now. Converts to the Dunker religion are pretty rare. You know, there's not a whole lot of people saying, oh, please sign me up, I want to be a Dunker. Dunkers who marry non-Dunkers often leave. So we have this, sociologists would call this a religious isolate, a human population that, because of strongly held religious beliefs and cultural traditions, is just a bit out of the mainstream. 1950, a guy named Bentley Glass studies a population of over 200 Dunkers in southern Pennsylvania. And back at the time, you couldn't do DNA sequencing, but you could do blood typing. And you may know that humans have several blood groups. The ones that you're familiar with are the ABO blood group, right? That's your blood is type A, B, AB, or O, and the RH blood type, right? If you're RH positive or negative. There's actually a number of others. They don't normally come into clinical significance. They're not particularly important if you're just trying to match blood types for a transfusion. That might come into play if you're doing things like organ transplant compatibility, but in the everyday, they're not really of clinical significance. And one of them is called the MN blood group. And because it can be hard to distinguish this in speech, especially in recording, I'm going to use the NATO terms, and instead of M and N, I'll say Mike and November. Okay, so your Mike November blood group happens to be controlled by a single gene with 2 alleles. If you are homozygous for the Mike allele, you have type Mike blood. If you're homozygous for the November allele, you have type November blood. And if you're heterozygous, you have the genotype Mike November. As far as anybody knows, there isn't really any survival advantage in having Mike versus November blood. There's little clinical significance. Now, some of these obscure blood groups have turned out that they actually do give you some survival advantage or disadvantage. There's one type in particular called Duffy blood. And if you are Duffy negative, I think it's Duffy negative, you actually have a degree of malaria resistance that you don't have if you're Duffy positive. Duffy negative is very common in Africa because Africa, you know, at least certainly Central Africa has quite a problem with malaria. Anyhow, but as far as I know, Mike November doesn't have that kind of clinical significance. So what we're going to do for starters is see if this population might be in Hardy-Weinberg equilibrium. Now think about what that means. We talked about that last week. G.H. Hardy and Wilhelm Weinberg worked out that if a population met certain criteria, the frequencies of alleles would be mathematically related to the frequencies of genotypes in a very simple way. And if the population met that criteria, neither the genotype nor the allele frequencies would ever change. Population would maintain exactly the same allele and genotype frequencies for as long as it was in existence. Okay, so that's 2 parts of it. First of all, if a population meets these criteria, the allele frequencies and the genotype frequencies will relate to each other. 2, the allele frequencies and the genotype frequencies will both stay constant. Now, Where that gets more interesting is that if you look at a real population and you find that that those aren't happening, if you find the allele frequencies are changing, or you find the allele frequencies do not have that neat relationship to the genotype frequencies, then there is something interesting going on, because one of the Hardy-Weinberg conditions, at least one, is being significantly violated. And I mean, that's not a bad thing. It's not like it's illegal to violate the Hardy-Weinberg conditions. It means something interesting is going on with that population. Something interesting is going on that's allowing that population to change over time, i.e. evolve. So, anybody remember what those are? This is something that by Thursday you need to be able to do in your sleep. Yes?
No natural selection, no sexual selection.
Okay, no natural selection going on, that's one. No sexual selection, true, that's a part of the random mating criterion. Sexual selection is one way that that can be violated. There are some others, like inbreeding, which, you know, kind of weird to think about in humans, but, you know, plants self-fertilize all the time. Some of them do. The population's got to be really large. What are the others?
All genotypes of equal fitness.
Okay, well, that's another way of saying no natural selection. Yeah, we said that. That's good, but that's two ways of saying the same thing. So big population, random mating, no natural selection. What else? There's two more.
No mutation.
Okay, no mutation. And the last one is, drum roll.
No immigration.
Yes, no migration in or out. So before we do anything, how likely are the dunkers to fit these? Well, first of all, he's studying a population of over 200 dunkers, but as of 1950, that's a sample of a larger population of about 3,500. I'll try to go into a little more detail as to exactly how big a population has to be. I mean, in theory, to get no deviation from Hardy-Weinberg, the population would be infinite. So in any population that's not infinite, you'll always get a little bit of deviation from Hardy-Weinberg, but we'll talk later about how big the population has to be for that to be significant. So for right now, 3,500 may be big enough, but we'll get to that later. So let's assume right now the population is big enough. Do we have natural selection? Probably not. It might be really interesting to test for, but from what we know now, it doesn't look like we should have any natural selection. Is mating random? Are mates choosing each other by their blood types?
Yes.
Wait, you think there are dunkers that are saying, "Ooh, I really love you, but we can't get married and I don't want to have your babies because you're one of those November blood types and I only really go for Mike"? Okay, is this the kind sort of thing people are putting on their Tinder profiles? Okay, probably somebody is, but right, it's not really usual. Okay, so there's probably people are selecting mates without any reference to whether they have Mike November or Mike November blood. Okay, and that's basically the random mating criteria. So mating is almost certainly random, no natural selection. For right now, let's say the population's big. Mutation always happens. You never get a population that's completely free of it. I'll tell you right now that unless you've got a population of like the fungi that they found growing inside the Chernobyl nuclear reactor, Or, the fish just downstream from Arkansas 1 or something like that. If growing in a realistic population by itself, mutation is a very weak force. It's not realistically going to push you out of Hardy-Weinberg unless you give it a very long time to act. Maybe I can bring that up later, but by itself, mutation is pretty weak. It will cause very slight deviations from Hardy-Weinberg, but they're not likely to be statistically significant if you're just looking at a couple of generations. And then finally, is there migration in or out? What's that? Not very much. That's one reason why geneticists were interested in groups like the Dunkers. There may be a little, every so often somebody from the outside might join, but the Dunkers don't go out of their way to seek out converts. They tend to marry within themselves, among, families and culture that they know. So the Dunkers right now look like they're a pretty good candidate for being in Hardy-Weinberg equilibrium. So how do we see whether they really are? Well, first, class found 102 Dunkers with type Mike blood, 96 with Mike November, and 31 with type November. So please help me remember those names because I'm going to switch over to our friend the whiteboard. It's a little bit easier for people to see if you're sharing or you're watching this later. Let me see here, format, good, black color, and I'll crank up a nice big font. So what do we have? We have what, 102 people, oops, one, with type M blood. And their genotype is Mike. And we had what, 96?
Yes.
96 with, that were heterozygotes. And was it 31? And 31 people with type November blood, genotype NN. Okay, what we want to do is find the allele frequencies. And this is really easy. First thing to do is we just calculate the total population, which is just 102 plus 96 plus 31. Which I think comes out to 229. Am I right? Okay, 229 population. Sorry, in a dark room, I can't always see the keys. And everybody is diploid. Right? They've got 2 copies of each gene, one from mom and one from dad. Yes. So the total number of alleles that they've got is just 229 times 2, which happens to be 558. So we have 558, dummy.
458.
Me, 458. Okay, clearly caffeine is not kicked in. Clearly I picked the wrong week to quit methods. So that's 458 alleles, right? Because every person has 2. Okay, the frequency of the Mike allele is going to be, think about it, we have 102 people with 2 copies of the Mike allele, right? So 102 people with 2 mics means 204 Mike alleles, right? But we have to add the number of heterozygotes. So we have 96 people that each have 1 allele times 1, right? That's the total number of Mike alleles in the population. And then we have to divide that. Dang it. 2 plus 96 times 1. So we take whatever that number is and we divide it by 458, the total number of alleles in the population. Yes? So that's 204 plus 96, that's 300, right? So that's equal to 300 divided by 458, which is 0.655. Okay, cool. Let's go over here. Frequency of the November allele. Let's do this the long way. And then, of course, there's a very obvious shortcut. And that's going to be equal to 31 people with 2 alleles each. Let me add those brackets. 31 people with 2 alleles each, and 31 times 2 plus 96 times 1. All right, that's the number of November alleles in the population. And then we divide the whole thing through by the total number of alleles, which is 458. And that should be equal to 158 divided by 458. And that should be equal to what? 0.345. Did everybody get that? Okay, great. The shortcut is that these allele frequencies have to add up to 1, right? Because every allele is either a Mike or a November. So the allele frequencies added up together must add up to 1. So if you know one of them, you can just subtract that from 1 and you get the other. So 1 minus 0.655, right? The frequency of November is 1 minus the frequency of Mike. That's 1 minus 0.655, and that is, of course, 0.345, right? Because these frequencies have to add up to 1. So if you know one, you automatically know the other. This is not the way to answer the question, but if you want to check your math, you can check, does 0.655 and 0.345 add up to 1? And the answer is yes, they do. If you're doing this with calculators, there's always a chance they'll add up to 0.99999 because of round off errors, but you can pretty much ignore that. If they add up to 1, we haven't solved the problem, but we have confirmed that we've done the math right. Okay, with me there so far? All right. In problems like this, we abbreviate allele frequencies as P and Q. So I'm going to let P equal the frequency of Mike, and that's 0.655. And then Q is equal to the frequency of November, and that's 0.345. Remember those numbers, we're going to use them again. All right, that's the first part of the problem. We've calculated the allele frequencies. And I hope you saw how to do it. It's pretty easy if you just think about what you're doing. I'll tell you up front, if I seem like I'm going through this really slowly and being kind of condescending, I'm not trying to come off that way, but I've had too many students before who just utterly crash and burn on problems like this. And a common reason is that they'll memorize formulas, but they don't really know what the formulas are for. So they will plug the wrong numbers into the formula and get something with no bearing on reality whatsoever. You know, they get an answer that's equivalent to 2 + 2 = fish, or something like that. They get completely surreal results. And so if I seem like I'm going through this very slowly, it's not because I think you guys are idiots. It's because experience has taught me that this is harder than it may seem for some people to get. And, you know, I always think about ways in which I can improve on this. You know, I certainly don't want anybody to bomb the next exam, but I do want to make absolutely sure that everybody sees what I'm doing with this. I'm not just going to give you a formula and say, just plug the numbers in, because if you don't understand what the formula means, you'll plug in the wrong numbers. And people have trouble, some of them, keeping track of the difference between frequencies of alleles, frequencies of genotypes, and frequencies of phenotypes. Like I said on Friday, make sure you've got that down absolutely cold. You know, go back and dust off your genetics notes if you have to. It's important. Okay, so remember those numbers, 0.655 and 0.35. And if we, not doing a poll, and if we go back to the practice problem, that's the answer for part A. Part B says we calculate the expected numbers of people who would have each blood type if the population were in Hardy-Weinberg equilibrium. If the expected figures don't match, suggest why this might be the case. Okay, so let's go back to our whiteboard and let me see, I'm going to erase, that's not how to do it. How do I do it? How does he do it, folks?
What are you trying to do?
Oh, get the stupid cursor to pick up text that I've already written and erase some of it. Okay, great, now I just erased the whole thing. Okay, let me put the relevant bits back up. We had 102 Dunkers with genotype Mike, right? 96 that were Mike November, and 31 that are November. Yes? All right. We'll set P to equal the frequency of the Mike allele, and we established that that is 0.655, and Q is the frequency of the November allele, and we established that's 0.345. Okay, if the population's in Hardy-Weinberg, what would we expect? Hardy-Weinberg predicts that if the population's in Hardy-Weinberg equilibrium, that the frequency of the Mike genotype is going to be equal to the square of the Mike allele frequency. It's going to be equal to P squared. I'm assuming there's a way, let me see, is there a way I can, there's probably a way I can turn that into a superscript, but just pretend for a moment that's a small p up and to the right, or small 2 up and to the right of p. So if we're in Hardy-Weinberg, then the frequency of people that are homozygous for the Mike allele ought to be the square of the frequency of the Mike allele itself, which is going to be equal to 0.645 squared. And if somebody's got a handy dandy calculator, you can simply plug and chug. That's going to be equal to what? Somebody who's got a calculator handy. In lecture, you can use your phone. What's 0.645 squared? Let me think. What would be 0.36, but somewhere between 0.36 and 0.49. So 0.416. Okay. It's going to be 0.416. Another way of saying the same thing, if this population's in Hardy-Weinberg equilibrium, if it meets all those criteria, then 41.6% of the population would be expected to have the Mike allele. Yes?
I've got 0.429, that's because you wrote 0.645, so this is 0.655.
0.655. Oh, okay. Okay, 0.655 times 0.655, and you got 0.429.
Yes.
Okay. Okay, so 42.9% of our population would have Mike blood if the population is in Hardy-Weinberg. Okay, with me there so far? All right. If we're in Hardy-Weinberg, the frequency of heterozygotes, Mike November people, is going to be 2pq. So that's going to be 2 times 0.655 times 0.345. And 0.655 times 0.345 is going to be 0.2 something, and you multiply it by 2, so it's also going to be 0.4 something. What do we got? 2 times 0.655 times 412? 452, okay. 452. Okay, so if the population's in Hardy-Weinberg, then 45% of the Dunkers should be heterozygotes. Yes? What's up? You got it? Okay. And then finally, the frequency of people with the November genotype should be equal to Q squared. And that is just 0.345 squared. 0.345 is going to be 0.1 something or other. What is it? 119. So 11.9% of the Dunkers should have type November blood if we're in Hardy-Weinberg equilibrium. Okay, a quick check. And this is not how you solve the problem. It's a way to check that we did the math right, is to add 0.429, 0.452, and 0.119. All of these ought to add up to 1. Or if you want to do them as percentages, all of these have to add up to 100%. So just to check that you did the math right, you can add those, and 20 carry it to 0. Yeah, they should all add up to 1 exactly. Or in some problems, they'll add up to 0.9999 simply because of rounding error. You can ignore that. All right, so if our population is in Hardy-Weinberg, this is what we should see. That's our expected. I usually don't make people do this in an exam situation, but I could always make you do a simple chi-square with 2 degrees of freedom, because these are our expected values. Now, what is our observed values? That's how I do that. Okay, our observed values are frequency of Mike. We have 229 people, and that's just going to be equal to 102 divided by 229. Right? That's the number of people, that's the fraction of people that actually do have the genotype Mike. What is that? What's 102 divided by 229? Sorry, 0.445. Okay, the frequency of heterozygotes in the actual population is 96 over 229, which is 0.419. And the frequency of November is going to be equal to 31 divided by 229. 29 is going to be 0.135. Okay, so on the left, we've got our observed. That's the real data. That's the actual distribution of genotypes among a sample of dunkers in 1950. On the right, we've got our expected. This is what we would expect to see if the population is in Hardy-Weinberg equilibrium. Now, they're very close to being in Hardy-Weinberg equilibrium. We're not getting anything that is totally radically different from the predictions of Hardy-Weinberg. I'm not going to make you actually do this, but in the real world, we do a statistical test here. And actually, we will on the lab data that we're going to gather tomorrow. I am going to make you do, I think we're just going to use the chi-square test, which I assume you've seen before. Yes? You've all heard of chi-square? Okay. We could do this here and just use the numbers on the left side of the screen as our observed and the numbers on the right side as our expected. And I don't know what we get, but I think you can see just by looking that we're pretty close to being in Hardy-Weinberg equilibrium in this population. So that tells us that the population is close to meeting the 5 criteria, that it is, in fact, large. There's no natural selection. Mating is random. There's no migration in or out, and there's no mutation, or at least there is not enough of any of these things to make much difference. If we got something that was different, if the observed and the expected were significantly different, that would get interesting, because we know that at least one of the 5 conditions was being violated. Maybe the population is too small. Maybe there really is natural selection going on and we didn't suspect it. Maybe there is some random mating violation. Maybe, for example, maybe mics like to mate with mics and Novembers with Novembers because of some subtle difference in how they smell. You know, maybe at the subconscious level, mics might be attracted to mics. Or could we go the other way around? Maybe mics don't really like other mics and want to get it on with Novembers. I don't think there's any evidence for that, but things like that do happen. I think our sense of smell plays a greater role than we realize in deciding mutual attraction. I think there's actually evidence for that. We've got more sophisticated smell receptors than we realize. Not really my field, but something you could look into, I guess. Anyway, or if we got observed radically different from expected, we might find that there's more immigration in or out of the dunkers. It wouldn't necessarily have to be people joining. Maybe the female dunkers are all sneaking down to Philadelphia for wild times and their husbands don't realize it or something like that. For the record, I don't think that's actually happening, but it could be that there's more mating outside the group than anybody realizes. I don't know. I don't think it is. We don't have evidence for it, but it is a possibility that we might have to keep in mind if we did get a significant difference between observed and expected. Okay, am I making myself fairly clear? Let's quickly look at the last part. Remember those frequencies, that the actual frequencies of Mike are about 45, 42 for Mike November, and 13.5 for November. And then our allele frequencies are 0.655 and 0.345. Make a note of that. And let's go over to the problem. Okay, in Germany today, about 30% of the population has type M, 50% has type Mike November, and 20% has type November. Okay, in the eastern US, the figures are almost identical. And even though the Dunkers are pretty close to being in Hardy-Weinberg, they do have a different genotype frequencies from the population that they came from, as well as a different allele frequency from the population that they live among now in the eastern United States. So we kind of expect that if there hasn't been much migration in or out of the Dunkers. You know, if the Dunkers were freely intermarrying with everybody else on the East Coast, then you might expect their allele frequencies would come to match the allele frequencies of people on the East Coast. But why are the Dunkers genotype frequencies different from the frequencies of people in Germany? You know, why do we have 30% of Germans having blood type Mike, but over 40% of the Dunkers having it? And why have we gone from 20% of the Germans having type November to what, 13% of the Dunkers? And in this case, there's no single fixed answer, but there's a couple of possibilities. This one you don't have to do calculation, just think about why those allele frequencies might be different between Germany and the Dunkers today. Okay, different population sizes. Okay, what would that do? Okay, it does, but let's jam on that a little bit. Okay, I'll give you one thing that we haven't talked about. If you have a population that's small, too small to be close to Hardy-Weinberg, what happens is that allele frequencies can fluctuate randomly, and you get change in allele frequencies for no particular reason other than chance. That's a phenomenon called genetic drift. So if the Dunker population is small, especially over many, many generations, you'll get Dunker allele frequencies diverging from the host population just by luck of the draw. So genetic drift is a possibility, and we'll talk probably on Wednesday. I won't make you calculate it, but we'll talk about in more detail as to how to detect that. What's another possibility? Okay, migration, what direction? Okay, migration from the general US population by itself isn't going to change. Well, I guess it might change that. Okay. All right. It's possible that the Dunkers have had contact with other people in the past.
No, Germany and the United States.
Okay,
And then the Dunkers stay by themselves. Because there's more nighttime than
Mhm.
the other ones. This is they're already between them. So that's fine.
okay, you're close to something. I think you're right, but take it a little further. You know, here's a hint, there weren't very many Dunkers. You know, there've never been a whole lot of them. And there weren't very many that made the trip to Pennsylvania because, you know, it's expensive and dangerous to cross the Atlantic in a sailing ship in the early 1700s.
Inbreeding could happen and mutations
Okay,
could.
yeah, inbreeding could happen. For reasons I'll talk about later, we don't actually see a strong breeding signal in the Dunkers, but it is a possibility. I'll talk a little later about how to detect inbreeding. So it's something we ought to look for. You're not wrong. Mutation possible, but bear in mind that by itself, mutation is really weak. By itself, mutation takes a very long time, longer than this, to push a population out of Hardy-Weinberg. But think about this, we've got a very small founding population. What are the odds that the founding population of just a handful of Dunkers was a perfect representation of the German gene pool? See what I'm getting at now? If, I don't know what the original size was, but let's say 50 Dunkers sailed to Pennsylvania in 1700 and don't remember, it's possible that 40% of that founding population had type Mike blood simply by random draw. Okay, a large German sample, you'd expect 30%, but maybe just a few extra people on that ship just so happened to have Mike blood simply by chance. That's a phenomenon we'll talk about later, and it's called the founder effect. I don't know about the Dunkers, but I can give you a real world example from where I grew up. I'm actually from South Louisiana, from a part of the country that traditionally used to speak French, although these days pretty much everybody speaks English. There's a unique culture down there. They're called the Cajuns, and they've got the best food and the best music. Really cool place to visit if you're ever down that way. Round about 1980, they started detecting cases of a rare genetic disease called Tay-Sachs syndrome around the towns of Eunice and Kinder, a little north and west of where I grew up in the city of Lafayette. And Tay-Sachs is very rare in the general population. It's more common among Eastern European Jews. But here it is popping up among the Cajuns, who are devoutly Catholic. They're not Jewish. They're not closely related to Eastern European Jews, as far as anybody knew. So why are we getting this cases of Tay-Sachs syndrome? Well, some geneticists went down there and they traced everybody's family trees and, you know, went from church to church in South Louisiana, you know, tracing genealogies. And it turned out that one of the French population that had settled that part of Louisiana just happened by, you know, stupid, rotten, blind, unfeeling chance, just happened to be a carrier of Tay-Sachs syndrome. And that person had kids, and they married other kids, and they had kids and married more kids. And eventually, even if people aren't trying to inbreed, this will happen. Eventually, if you give it enough time, two distant cousins married and had kids, and they were both carriers of the Tay-Sachs allele, and they had a child with Tay-Sachs syndrome. Now, Tay-Sachs means progressive degeneration of the nervous system and death by the time that you're about 4, if not sooner. It is a very unfortunate and pretty nasty genetic disease to have. So people with Tay-Sachs can't reproduce, but people who are carriers can. And because you just happen to have one person in the small founding population of the area around Eunice and Kidder, Louisiana, 300 years later, people started seeing a rise in the incidence of Tay-Sachs syndrome. In fact, it had been going on for many years before the 80s. But people didn't recognize it for what it was. They just knew that some babies would just tend to get sick and die, and there was nothing anybody could do. And it wasn't until the 80s that geneticists got down there and worked out exactly what was going on. Now that they know what's going on, they can genetically test people. And if a couple are both carriers, they can make the decision whether they want to have children or not. So, you know, the risk of having a Tay-Sachs child is something that can now be at least managed. But that's an example from where I grew up of the founder effect. And it could be happening here. If the small group of Dunkers that settled in Pennsylvania just so happened to have a few more people than average that had type Mike blood, then their allele frequency might be higher for no reason other than luck of the draw. Be it said, there's examples like that everywhere. Somebody estimated that every human being is carrying something like 3 to 5 recessive alleles that would be really severe if we were homozygous for them. The reason why people manage to get born is that the majority of times 2 people are not carrying the same recessive alleles. For all I know, I could be a carrier of Tay-Sachs and my wife could be a carrier of sickle cell. But our kid might not be a carrier of either one, and he won't get either disease because I'm not carrying sickle cell and she's not carrying Tay-Sachs. Or for those diseases, substitute Charcot-Marie-Tooth syndrome or Duchenne muscular dystrophy or Becker's muscular dystrophy or any one of thousands more severe, rare but severe genetic diseases. The reason why we have as many healthy births that we do is most couples aren't carrying the same set of recessive with severe effects. But yeah, what I think is likeliest here might be the founder effect, but there could be other things. There could be other factors. And that's one where if you see that on the test, I leave a fair number of questions, fairly open response, where if you can make a coherent case for a particular answer, I'll give you credit even if it's not the answer I had in mind. I try not to make you folks become mind readers. Okay, on that note, we'll do another one after the break. I've got 10:03, so I'm going to stop the recording.